Okay, let's come to the third part of our machine learning tutorial, namely logistic regression. So logistic regression is the easiest method for classification. Now, for classification, what we want to do is we have an input example, and instead of predicting any continuous number, such as the house price, we want to classify it into one of two or more different classes. For example, an image representing a dog or a cat, or an email being spam or no spam. So let's say we have two classes. Why can't we just use linear regression and, for example, say if y is equal to 1, we have spam. If y is equal to 0, we don't have spam. Now the issue with that is going to be that the predicted value that you get, because linear regression is a straight line, can be less than 0 or larger than 1, and it's not clear how to interpret that. So what we want is we want a prediction that's somewhere between 0 and 1. If we do it, like shown here, we can interpret y as a probability. For example, if y is equal to 0.8, we can say there's a 0.8 probability or an 80% probability of our training example being spam. What does this function look like mathematically? So first, we want to take our features x1 to xm, and we have parameters θ0 to θm, and we generate the z-score, which is very similar to the functional form from linear regression that we saw before. Once we've calculated z using these parameters that are to be found, we can plug it into this function here, 1 over 1 plus e to the minus z, which you can see depicted in this coordinate system. And the idea is that we can interpret this as a probability. Now, e is going to be the exponential number. So e to the minus z, if z is very large, this is going to be close to 0, and the probability is going to be close to 1, but never equal to exactly 1. If z is very small, so minus 10 or something, e to the minus z is going to be very small. If it's going to, because we have a minus sign here, it's going to be very large, and the probability is going to be very close to 0, but not exactly equal to 0. If z is equal to 0, it means we're undecided, because e to the power of 0 is 1, and we have 1 over 2 as the probability. That's this point. Okay, let's say we have data points that are males or females, and we have two features. We have the person's height and their weight. So generally speaking, males are associated with a larger height and a larger weight. Now, you can see here this line represents the decision boundary of a logistic regression applied to this data set. So if a point lies on this side of the line, we would interpret or we would predict this point to be a male. If the point lies on this side, we would predict it to be a female. Why this decision boundary? Well, this is exactly this line here, and this is a straight line. So in this case, we would have θ0 plus θ1 times height plus θ2 times weight. So we would have 3 parameters. Okay, now in the same way as before, we also have to train the model. And this time, in fact, you can't use calculus. For linear regression, you could set the derivative of the cost function to 0 and solve. But here you actually have to use an iterative algorithm, and you can use gradient descent as before. So what is the cost function going to be? For linear regression, we had squared error. Now, for reasons I won't go into, it makes a bit more sense to use a different cost function. So let's consider two cases. First, the true class being equal to 1. If the true class is equal to 1, we want the probability that is predicted to be close to 1 as well. If we do minus log of the predicted probability, if the predicted probability is close to 1, minus log of it will be very small, will be close to 0. If the predicted probability is close to 0, it would shoot up to infinity, which makes sense for our purposes. So we'll have a very high cost. Now we can flip this function around 0.5 to obtain the second case. If y is equal to 0, we want a predicted probability close to 0. So we want to be here. If the predicted probability is close to 0, the cost will be close to 0. If the predicted probability is close to 1, we will get log of something close to 0, so it will shoot up to infinity. We can put these two cases together as such. If y is equal to 1, 1 minus y will fall away. You will be left with this part. If y is equal to 0, this part will fall away. You will be left with this part. So this is how we cover the two cases. And we want to minimize this. And gradient descent is the easiest way of doing it. Okay, so this is for two classes. What happens if you have more than two classes? For more than two classes, we can extend simple logistic regression with two classes by generating probabilities for all k classes. And we would use a slightly different cost function. So essentially, instead of having one probability here, we would have multiple probabilities, and the cost function would combine them. Also, the decision boundary wouldn't just consist of one line, it would consist of multiple straight lines. But the basic idea is very similar. Okay. Now, before we said that a regression model can be evaluated using squared error, how can we evaluate a classification model? Of course, again, there are multiple ways, and the easiest one is just look at accuracy, meaning you look at all examples that you predict on, and you count how many are correct. That's going to be your accuracy, the percentage of correct classifications. However, sometimes you want more, and this can be the case if you have imbalanced classes, meaning one of the classes has a lot more examples than the other class, or if you have different misclassification costs, meaning it's much worse if you classify, let's say, a cat as a dog than a dog as a cat, for whatever reason. In this case, we can use a confusion matrix. What's a confusion matrix? The rows represent the true class, and the classes here are labeled as 0 or 1. So is it actually a 0? Is it actually a 1? The columns represent the predicted class. Is it predicted to be 0? Is it predicted to be a 1? This cell represents the true negatives, Tn. These are all the examples that are actually negative, so 0, and are also predicted to be a 0. This cell is the true positives, the examples that are actually positive and are also predicted to be positive. This is the false positives, the examples that are actually false but predicted to be true. This cell is the false negatives, the cases that are actually predicted to be, that are actually a 1 but predicted to be a 0. Okay, once we have this confusion matrix, we can go further. Now, in general, when we classify using logistic regression, we say if the probability we get out is larger than 0.5, we predict an example as class 1, otherwise as class 2 or the other class. But we can change the threshold. So for example, we can say we only want to predict class 1 if the probability is equal to 0.8. In that case, we will get a slightly different confusion matrix. Here is where the receiver operating characteristic curve comes in, or RC curve. The idea is to generate a confusion matrix for every possible threshold between 0 and 1, and calculate these two metrics here, the true positive rate, which is the number of true positives, divided by the true positives plus the false negatives, so all the positive examples, and the false positive rate, the false positives divided by the false positives plus the true negatives, so all negatives. If we have these two metrics, we can represent them as a point in this coordinate system. On the x-axis we have the FPR, and on the y-axis the TPR. So let's say for a threshold of 0.6, we'll get this point here. We can generate points for all the thresholds, giving us this blue curve. Ideally, you want your false positive rate to be very close to 0, and your true positive rate to be close to 1. So a perfect model would have a point up here. Now we can measure the area under the curve, meaning this area here. If this area is close to 1, 1 will be the maximum area, then we have a good model. However, if it is close to 0.5, it's no better than random guessing. This line represents a baseline where we wouldn't take the features into account, but we just make a random guess what class an example is. So if it's 0.5 or close to 0.5, then you don't really have a useful model. If it's very close to 1, you have a very good model. And this is called the area under the curve. And what this does is it evaluates a model using all possible thresholds at the same time. So in a way, it's a more comprehensive measure than just accuracy.